give you a linked list, you insert, right, or you delete. It's not ambiguous. Now, in a binary tree, it is. Now, so that is a correct understanding. You don't know, okay? That is just like, what is the next number in lottery? You don't know, okay? So you don't know is the correct understanding. Now, the other is how to traverse a post-order traversal. Say I have an expression here. 3, 6, 1 plus star. Now, ultimately, I use a stack to do that for a machine. Now, how actually do I do that? I see a 3, I push to the stack. I see a 6, I push to the stack. Okay. I see a 1, I push to the stack. So the stack, okay, is going up. This is the top. Okay. Top. Okay. You remember stacks, right? Now, and then I see a plus sign. Now, I don't push a plus sign because it's operator. Okay. Whenever you see an operator, the rule is that you will pop two numbers. So here, I will pop 1 and 6. Okay, so 1 and 6 will be popped and they will add it together. It will become 7. And I push it back to the stack. Okay, so I pop 2 and push 1. Okay, and ultimately, I have a multiplication again. Okay, and I don't push it. I pop out two numbers, 3 and 7. Okay, and now I will be 21. Oh, sorry, y is smaller. 21. Okay. So ultimately, when I finish the expression, I will have my result inside the stack. Basically, the stack originally is used like that. In many mathematical operations, okay, you always have the stack ready to calculate something. Now, it will appear somewhat strange to you, but it is very not easy to program in a programming language, right? So that's the key point of a post-order traversal. Okay. Now, and also pre-order and post-order notation, the Polish and reverse Polish notation, are much easier to pass, okay, into a tree. Okay, you can imagine now if I look at the post-order traversal tree or pre-order traversal tree, it's much easier to create a tree. Now, I leave it to you as an exercise, okay, for advanced students, okay? Because the parsing programs is very hard. Okay. Parsing program means you convert this into a tree. That is very hard. Okay, usually that's very hard. Now, so a binary expression tree, we look at a way in which the binary tree is really used because what we have here is a binary relationship. Okay. Now let's look at a tree in which it is originally not a binary relationship, or at least too abstract. Okay. But then we will still use it anyhow. The binary search tree. Now, a binary search tree, as again, is very like a decision tree that I talked about last time, right? Friends, non-friends, targets, okay? And among friends, hopeless friends.
Yes.
Okay?
Boyfriend.
Yeah. Well, when you are a friend, you don't call it boyfriend. It's a bit strange, okay? And targets, then you would possible targets or impossible targets. Say some K-idol pop star or something like that. So a tree is also a decision. What decision can it make? Larger and smaller, right? So supposedly, this is pool, okay, not pool, okay. So here, we have a binary search tree. Now, a binary search tree is a binary tree with additional constraints. Now, some of you can think like that. A binary tree is ambiguous in its operations. So a more mathematical mind will understand that it is partial, the definition. It's incomplete. Right? When you cannot pinpoint something, that means its definition is too loose. So one way to increase it is to add restriction. Okay? When you add restriction to a binary tree, then suddenly your operations can be more unambiguous. So here, a binary search tree is a binary tree with the extra restriction. Now, each node must contain a key that can be ordered. Okay? You can be searching names, you can be searching numbers, I don't care. Okay? But can be ordered. And all keys in the left subtree must be smaller than the parent node's key. All the keys, okay, on the left is smaller. And all keys on the right tree must be larger than the parent node's key. Okay? And I assume because I use the word key now, you'll be very sensitive when I say the key, not the data, it means it is unique. Okay, a key is unique. So just like your student ID, it's impossible for two of you to have the same student ID. So no duplication of keys are allowed for a binary search tree. Now, so we have a binary tree definition, and now we have added additional definition. Then we have a class of trees, subclass of trees. We are different. Okay, which of the following is a binary search tree? So assuming you guys have more evaluation for your tutors. Now anyway, here A is 60. And we have 30, 40, 10 on the left tree. Okay. And we have 70, 90 on the right tree. So on the top level, okay, it's okay. Now, but this is not the end. We also need to look at the subtree. 40 is greater than 30. Okay, and 10 is less than 30. Okay, so it is a binary tree, binary search tree. It fulfills all the extra rules. Now here, this guy, 60, and we have 10, 30, 65. Now, despite the fact that on the first survey level they are the same, the 65 is greater than 60. So this is not a binary search tree. 65 belongs to the left subtree, but it is greater than 60. It should be on the right subtree. So this is not a binary search tree. Okay. Now, but you will always see that. Look at this linked list. The left subtree 4, 2, 1 smaller than the right subtree, right? Oh, so our dearest linked list appears again. It is still a favorite binary search tree. Okay. Now you will definitely notice that the binary search tree itself slightly more restrictive. Okay, but it's still okay. Cannot prevent the linked list. But let's not think about it. What is the use of a binary search tree? Now, obviously, you have seen this before, right? When you want to search for a number, say I want to search for 40, I can use the binary search tree to search. I look at the root node, it's 60. Then, I know that I will need to go to the left subtree because the left side is smaller. Then I go to 30. I know that it's on the right subtree because 40 is greater than 30, then I get to 40. Right? Even if I search for some numbers, say now I search for 45, which doesn't exist. I go for 60, 30, 40, and 40 is a leaf node. I immediately know that there's no 45. Okay? So here I have a binary subtree, a search tree that I can use to do a search. Now obviously you have seen this kind of search before. Yes, it's very similar to binary search, right? It's also very similar to quicksort, okay, in which you are trying to put everyone on the same side and recursively put everyone on the right side. Now, so here it is capturing the spirit of the searches and all the sorting we have been doing so far that is quickest, is using a tree, okay, to help us do this. Now, how many times do I need to go through? Now, ultimately here, I 1, 2, 3, 4, 5, 6. But I only need 2 times to 3 times to find out. Now, you have done the lab exercise before. How many times do I need to go through? Now, in a binary search tree, by visual, you can realize that the maximum number of times is the depth of the tree. Right? So, if the tree looks nice about it, imagine it's 1 million nodes. It will be very healthy, right? You having a very quick search. Now, but of course, when you have a linked list, then again you will do an order of n. Okay? So I want the tree to be balanced. If it is balanced most of the time, it looks really like a tree. I can save time, and I can do a search. I can do a lot of things easily. So here I say the power of a BST lies in it is sorted, and we can do searching on the tree. Okay. Now, if you want to print out things in order, I can use an in-order traversal. Look at here. I do an in-order traversal, 10, 30, 40, 60, 70, 80, 90. Sorted. Now, on this, 10, 30, 65, 60, the not sorted. Okay, so when you do an in-order traversal on a binary search tree, you get things in order. Now, of course, some of you will already realize that is why we call that an in-order traversal anyway. Because recursively, everything is in order. So ultimately, not only you have a binary tree that can allows you to search. This binary tree also allows you to print out things in order, which is very important nowadays, right? You sort everything in order, you do everything in order, and suddenly you realize on the internet or on applications, when you see an ordered list, it's not really an ordered list. Most of the time, it's actually a tree. Okay, and we are doing an in-order traversal for you. Okay, you can imagine Amazon and Taobao. It's impossible for them to really keep up. Backend is a database, and that database is a tree of some sort. Not this one. Okay, it's more complicated. But even it's a tree of some sort. So that when you search, you just go on and then search different nodes. Okay. Now, of course, you have seen that, as I say, it's binary search. Now, of course, in binary search, it's slightly different, right? In binary search, if you remember, I pick the middle node, right? And then I left, and then right, and then I go on. Now, in a binary search tree, I'm not so fortunate. I must start with the root. So if your tree is good, then my binary search will be very good. If your tree is degenerate into list, then I simply is doing a list linear search. Okay, so that's the difference. Now, of course, doing a binary tree is not easy. Why? Because ultimately, I have extra restriction. Now, if I have this extra restriction, my benefit is that any search is order of log n. Log n is very good. 1 million to a log, still acceptable, right? And another way is that we recognize that the height of the average BST is order of log n. And so, actually, many operations you can imagine is related to this height. And if it's very imbalanced, and the worst possible height is order of n, right? So the worst possible operation is order of n as well. Now, it's easier said than done. Okay? Let's look at insertion. Just now we say when you insert, you have many ways, right? Now in a binary search tree, you only have one way. Now when you insert, you do a search. Say now I want to insert 35. Okay? Then I will go to 60. And 60, I know that is less, so I go to 30. And I know that is larger, and I go to 40. And 40, now I know that there's no 35 here, right? So I will become the left child of 40. Okay, so insert is very easy. That's why you need to do insert in the lab. Okay? Insert is very easy. You do a search, and you end up on that node, and you insert at the right place. Right? Now, then it will guarantee it is a good way. So here, supposing now I insert 50. I will look at 60. In 60, I know it's less than 60, then I go to left tree. In the left tree, I know it's on the right. In 40, I know it. So ultimately, this is what it looks like. Now, sometimes you notice that in some textbook and example, we will draw the tree this way, so that you can see this is a binary search tree. Easier to see. 10, 30, 40, I leave the space of 50, and then until you see the 60. You see, you stretch the whole thing a little bit, so that you will see the in-order traversal easy. Okay. Now, here, you see the 10, 20, 30, 40, 60, 70, 90. Also indicates that when we insert it correctly, it will remain to be a binary search tree, and there's only one way to insert it now. Right? Compared to what we said just now. If I have random binary tree, then I can insert anywhere. Right? But here, I have only one place to insert. Now remember, for a binary search tree, it's a key. So there's no duplicates. Okay? You can do duplicates, but it will not be easy. Imagine that it is a lot of duplicates. 20, 20, 20, 20, 20. Then your binary tree will a bit messed up. Now the second part, you have insert, then you have delete. Okay? Now delete is the harder part. Now in your binary tree, you need to delete, but then you need to maintain that it is a binary search tree. Now we have three cases. The node to delete is a leaf. the loop to delete have one child, and the loop to delete have two children. Okay, so look at it. Of course, the first case, loop to delete is a leaf. We like leaves, because leaves is the easiest, right? In a real tree, you delete a leaf, gone. Okay, so case 1, I want to delete 3, it is gone. Okay, that is why when you delete, okay, when you are in a company, when people cut you, it's easiest when you are the lowest, okay, right? The junior cut, okay, nothing has to be done, okay, easy. So it's very, no, we don't, usually nobody notice that you are gone, okay? You are cut, nobody knows you are gone. Now, that is something slightly harder. Now you are a kind of a senior. You have someone working for you, okay? So if I remove you, you have your team, and I will replace it. So here, if the node have one child, okay, that is very easy, right? When the node is one child, say now I want to delete 4, okay? You only have one child. That child cannot be left alone. So there are only 2 ways. In reality, I can also cut 3, okay? Gone, bye, your whole team is gone. But in reality here, I need to promote 3. So now 3 will take the place of 4, okay? So again, this is still okay, right? One child, okay? I promote you, okay, up 1. Okay? This is the ideal case you want when you do a job. Okay? Your boss is gone, and you are the only one under him. Okay? Right? You get promoted immediately, most of the time, unless you are very bad, okay? Then you transfer to other teams. Okay? Now, the toughest case, you really set a manager, and there's a whole team of people, okay? And you need to promote one of them. Now, luckily, we are only a binary tree. Right? You see the case here. Now, when the node have 2 children, when I remove that node, who do I promote? Now, we have 2 choices. We can use the minimum key in the right subtree. Right? Because the right tree has to be larger than everyone. So when we want to promote, we can get the minimum on the right. Or we can get the maximum key in the left subtree. So because the left subtree has to be less than yourself. Everyone in the left subtree has less than yourself. So I can get the maximum to the left and promote him, and it will remain to be binary search tree. So in our example here, if I now try to delete 2, I still have 2 choices. Okay? I can promote the minimum on the left subtree. Okay? The left subtree has 4 and 3. So actually, I will promote 3. Okay? It will end up at 1, 3, 4. Now check again. 1 is less than 3, and 4 is greater than 3. So it's still a binary subtree. Okay? 3, 4 is the right subtree. The minimum is 3. Okay? Now, on the other hand, I can try to promote the maximum in the red subtree. Luckily, on the left subtree is 1. Okay, so 1 you get promoted, and if you look at it, usually it's slightly hard to see, but if I draw it clearly, it's 6, it's 1, 3, 4, 6, 8. Okay, now this tree looks a bit ugly, right? Already, you see the more you delete, okay, the more it becomes more and more ugly, but it's still a faded tree. Okay, 1, 4, 3. So 3 and 4 both greater than 1, so it's on the right side. Okay, and 1 is the root. So you see here, I can delete, instead of almost infinite amount of variations, I still have, right, 2 variations that you have. Okay. Anyone with trouble with delete? Now, so even for you to delete a node, okay, the code is very long, and you need to do it in the lab. Okay, anyway.
Right.
But it's okay. This is perfect exam question, right? It's very easy to make, even if you're a teacher, right? You give a cheat. Delete this, done. Okay, yes. So you need to do that, okay? By mind or by whatever, then it's okay. Okay? Then I let you pass, okay? Now, so you see here, with delete, insert, and traverse. Now, remember, in this case, a pre-order traversal no longer have any meaning here. So say here, this binary tree, I do a pre-order traversal, 60, 30, 10, 40, 70, 90, means nothing. Okay, so for a binary search tree in this specific case, an in-order traversal is the only traversal that makes sense. Okay? So, as I have said in the beginning, a binary tree is different depending on your implementation and application. So if your binary tree is used elsewhere, then suddenly all the rules will be different again. Okay? So that's why in your job interview, people like to talk about binary trees. But I give you a hint. Every time it's still binary search tree. Because the whole world is just searching and sorting. Okay? All the e-commerce applications, whatever, they are all doing searching. So most of the time you're doing binary search tree. If you meet a computer science boss and they kind of stick to what they learned in the when in the university, they will test you on the binary expression tree. So that's why I also test you on the binary expression tree. That's usually the two kinds of binary trees they will talk about. If they do another kind of tree, then considering apply to other jobs. Because they are sadistic and just want to torture you. Okay? Now anyway, any questions? Now, a binary search tree is very useful, and basically it's the basics of every kind of sorted and searchable thing that you use in daily life now. Now, why is that? Let's look at our cheat sheet. Now, if you look at the binary search tree, Now, it's access. Okay, I want to access a certain element log n. I want to do searching log n. I want to do insert log n. I want to do a delete log n. Okay. It has order, so it is access. Remember, access is to access in certain order, and you cannot do it with hash table. Hash table has no order. Okay, remember. And search is that I have something in mind and I want to search it, log n, insert delete log n. Now compare with everything you have learned so far. Array is fastest in access, right? Or well, fifth element. Okay, then I know the address, I get it. Search, okay. Array is not very good in search, so it's order of n. I need to know. Array is bad in search, it's bad in insert, it's bad in delete. If you remember, if you have an array, you need to move everyone, okay? Now, so array only have best in access. Now, a stack is best in insert and delete because you just put on the end, okay? But then it's not very good in access and it's not very good in search. Okay? Basically, you don't do this in a stack. Now, linked list is bad in access and search. If you remember, if you go to a certain item, you need to go by link to link to link to link to link, right? You need to start from the head and then go through each of them, and it's order n, but it is actually very fast in insert and delete, okay? Order of 1. In linked list, in delete, you just remove the link and then, okay. So linked list is best in insert and delete. The nobody is best in everything. Now in hash table, it is very fast in search, very fast in insert, very fast in delete, all constant time, but it has no order. Okay. Now look at this guy, the binary search tree. It's actually what we call the average guy. He is not the best in everything.